Okay, so in today's lecture we are going to see a physical example which shows a catastrophic behavior, which is insect outbreak. Okay, so if you see in Canada, the eastern part of Canada, there is a budworm, and in that budworm they eat a tree, the balsam tree, and the thing is, sometimes it happens that the number of insects will grow more, and it will just defoliate the trees, and it's like it will kill most of the fir trees in the forest. Okay, and that will happen within 4 years. Okay, 4 years of time it will happen. So this problem has been investigated by a person called Ludwig. Okay, so and he analyzed this problem along with his co-researchers in 1978. Okay, and he considered this model by considering he considered this as a dynamical system. And if you see in the dynamical system, what are the state variables? The state variables are the population of trees, right? So the number of trees, and what else? Number of insects. Okay, because these are the variables which are going to change with respect to time in that dynamical system, in that forest, right? But that's a if we have two dynamical parameters, then we are dealing with 2D systems, right? But so far we have learned only 1D system, and we are going to reduce this 2D into 1D for the following reason. The reason is the change in number of trees is going to take very long time. Okay, so it's a slow time scale. This is going to, the change in number of trees is going to take very long time, or slow time scale, right? But this, related to this happened bit faster. Okay, so this is a fast time scale. Okay, so at that time what I could do is I could freeze the change in number of trees, and I could just do the analysis by considering this as the only variable. Okay, so that's how we are going to attack this problem. Okay, so this person Ludwig proposed the model, and the model is in the following manner, which is n dot, where n is the population of the insect, okay, which is equal to, so we know that the logistic equation, which is Rn, which is the birth rate, minus 1 minus n by k, right? The k is the carrying capacity, where after a very long time the n will reach the value k, right? But here this is the logistic equation. In this logistic equation he added a correction. Okay, so the correction he added is a function p, which is a function of n. So what is this function? So here he has considered the birth rate and the death rate. Okay, so which depends on the carrying capacity. On top of that, okay, on top of that, there could be some birds which could eat these insects, right? So he considered that term as well. okay. And one more thing, this carrying capacity K is gonna go up if the number of trees are going up, okay. But for a particular compared to the change in n, the change in K is going to be not that much, okay, because of this assumption that it's a slow time scale and this is a fast time scale, okay. So what we are going to do is we are going to do this analysis further by keeping this K value constant, okay, or like a control parameter, okay. But before that, let's see what is the function Ludwig assumed for this P, okay. The function which he assumed is the following: P of n is equal to b into n square divided by a square plus n square. So this is the function he assumed, okay. And where a and b are some parameters, okay, which are not going to change, okay. Let's plot this function and let's try to understand what does it mean. Okay, so here I have showed only the positive side of the n, because there is no meaning at the negative side, so we are just focusing on this side, okay, where if I change my a value, and this is how it's varying, and if I change my b value, it looks like this. So what exactly this function mean is the following, okay. If I have very small number of insects, okay, the p value is less, which means the predators, okay, or the birds will eat very less number of insects. So the reduction in the population of the insects due to this predators will be small, okay. But at the same time, if the number of insects are large, then that's going to increase, okay. The number of birds going to eat more. But at the same time, if the number of insects get very large, okay, then the birds cannot eat everything, okay. So it sort of get saturated, okay. So even though we have a lot of food, we cannot eat all the food, right. So it will get saturated. So that's the meaning for this term, okay. So now so this is the so this is the function we are going to analyze, okay. But the problem is we have 4 parameters. So r is one parameter, k is one parameter. In addition to that, we have 2 parameters like b and a, right. So now what we are going to do is we are going to do something and we are going to reduce the number of parameters. So we have already seen how to reduce the number of parameters. So the idea is writing this equation in a dimensionless form. So that's what we are going to do. So the first thing is what are the dimensions it has. So one is a population, okay. The n represents the population, so that's one dimension, okay. The another one is time, okay. Those are the 2 dimensions which we are going to get rid of. So the first thing is I'm going to get rid of this population. That I could do by dividing one of the parameter which has the same dimension like population. And if we see the k, the parameter k is having that dimension, and also if you see in this term A is having that dimension, so I could either divide this whole thing by k or by A. Okay, so let's choose A to divide this whole thing. Okay, so what will I get? So I'm going to assume that I'm going to assume a parameter x, okay, which is equal to n divided by A. Okay, so that this is a dimensionless parameter, but it's that value is proportional to the population. Okay, so in that case I will get it in the following form. Okay, I will also do one thing. Okay, if I will also divide this whole thing by b. Okay, so let me divide this whole thing by b. So what will I get? A by b. Okay, and instead of n dot I could put a x dot, right? And I have divided this whole equation by b, so this is what I will get, which is equal to r a x by b into 1 minus a x. Wherever I see n, I will put a x. Okay, by k minus, okay, so this term. Okay, what will I get? So I will have a square over here, and there will be a square over here, and those a squares will get cancelled, and finally I will have this form of that equation, 1 plus x square. Okay, so this is my equation now. Now if you see how many variables are there, so a by b is one variable, r a by b is another variable, and a by k is one variable. So by making the one of the dimension, which is the population, by reducing that dimension, I was able to reduce one parameter, but still there is one more dimension which I could reduce, which is time. Okay, so now what I'm going to do, I'm going to assume t, the time, which is equal to which is equal to tau by capital T. Okay, so if I do that, what will I get is the following. Okay, sorry, I have made a mistake. The actual assumption is tau is equal to t by capital T. Okay, where this capital T is the characteristic time scale. Okay, and if I substitute this one for this time dimension, what will I get is a by b capital T. Okay, and here it will be like x comma tau, which is equal to this whole thing. Okay, so these things are not going to change. Now what I'm going to do is I'm going to assume this capital T, because that I could choose as anything, right? If I assume that as a by b, okay, if I choose that as a by b, then I could get rid of this whole thing, and finally I will get x comma tau, which means dx by d tau, which is equal to this thing, which is a parameter. Let me call that parameter as r, okay. So r x into 1 minus, and let me call this parameter a by k as 1 by k, okay, 1 by small k, okay. So x by small k, okay, let's say that's a small k and this is a capital K, okay, minus x square by 1 plus x square, okay. So this is our equation. Now we have only two parameters, one is r and another one is k, and these parameters are also dimensionless parameters, okay. So this is like a parameter somewhat like a growth rate or birth rate of the insects, okay, and k is somewhat like a carrying capacity, okay, like a dimensionless carrying capacity, okay. And this is actually, if you see, k is k by a, right. So which means if number of trees increase, this small k is going to increase, okay. And this mentions what is the birth rate, okay, for that dimensionless variable. Okay, so in the next video we will see how to do the analysis. Okay, thank you.